exactly like how you draw the restriction, like what angle you draw the
No. The question is, does it matter what angle you draw the Lewis structure? Not at all. So this is a very common question in organic chemistry. We'll just draw like structures like this. So we ought to name things based on the longest carbon chain. So it doesn't matter how it zigzags. And so the longest carbon chain would be 1, 2, 3, 4, 5, 6 carbons here. And so we use the name hex, and then no double bond. So this would be hexane. But there's so many different ways you could draw the Lewis structure. And so a common question is, what is the carbon-carbon-carbon bond angle here? The carbon-carbon bond angle would be what? It looks like it's 90 degrees there, right? And so this is 90 degrees. However, this carbon-carbon-carbon bond angle is 180 degrees. But that's all wrong because those structures don't have to represent the structure at all. And so that's why we have the wedge dash structures and the molecular geometry drawings for this. And so sometimes what they'll try to do in chemistry is they'll try to draw the Lewis structure. So it is a little bit more accurate. But sometimes they won't draw the wedges and the dashes. They just draw lines here. Sometimes they'll draw the wedges and the dashes. So there would be different levels of this, depending on how you draw. Usually they'll just do this in shorthand. 1, 2, 3, 4, 5, 6. This would represent that. This is just a zigzag pattern of the carbon atoms. Was that it for the question? Okay. Were there other questions? All right. I inputted just one lab yesterday, which is experiment 1, and so it's going to take me a little bit more time. I'll put in the next experiment 2 tonight, and then maybe more. And so this week you'll have it up, except for 6 and 7. 6 and 7, you have to make sure that you wrote the heat equation, the ionic equation, and the NIE for the single and double replacement reactions. The other reactions, you don't have to do this. Just for the single and double replacement reactions that we did in lab. So, all right, if there are no other questions, then we're just going to continue with chapter.
Just a general question, but for the carbon ones, are we going to need to know that for like the exam or anything? Would you give us something that complicated?
What, to draw the three-dimensional?
Yeah, just like the
structure of
organic ones.
You'll have some organic ones. I mean, for example, can you do the hardest? What was the hardest one on the lab? Glycine. So you might have up to glycine. If this were Chem 1A, you might be throwing something harder than what you've seen.
So going back to the organic ones, I spoke with the tutor regarding like if there's an O and an H, sometimes they like to bond together rather than, is that always going to be the case or?
Not always the case because you have different structures. So if we look at this one, C2H6O, this is something I'm not going to ask you to do, but in organic chemistry, this would be like the beginning organic chemistry type thing. What are all the isomers for this structure? And so what you'd have to do is you have to think of all the potential Lewis structures that you can draw for this. And so there are two isomers for this one. One is the very familiar CH3CH2OH. All right, here, there are different ways we draw this. This isn't very accurate, or maybe it is. It depends on how you look at it, from what perspective and which, So a lot of people, what they'll do is they'll bend this because, they'll just bend it at 90 degrees. But 90 degrees isn't accurate as well. And so you'd have it straight like that or bent or kinked like that. And so here the hydrogen likes to bond to the oxygen, but carbon also bonds, so we can have this structure as well. And in that structure, all the hydrogens are on the carbons. And so this is ethanol, this is methyl ether. Both of these are common chemicals. And so it just, if it's an acid, then for sure we're going to bond the hydrogen to an oxygen. If there's no oxygen, then we're going to find the most electronegative element to bond it to. But if it's anything else, it may or may not bond to the oxygen there.
So which one's correct?
Both are correct. This is why something like this is not descriptive enough. Because especially when you get to, let's say that's 2 carbons. What happens when you get to 3 carbons, 4 carbons, 5 carbons? And the number of isomers just grows, and grows. And so, like in organic, this might be too easy. They might give you something with more, isomers that you have to draw out. And you don't want to draw ridiculous structures. So you always think, number one, you want the rule. What rule to be satisfied? The octet rule. And so, when you get to organic chemistry, some people forget the octet rule. And they come up with some ridiculous structures that don't even satisfy an octet. And so this is another reason why I'm not really emphasizing the expanded octet or the less than the octet. You got to focus on the octet and make sure that's the number one priority is to get an octet if you can't get an octet. And then number 2, we look at formal charge, and then C. And then when we get to more advanced structures, then you look for resonance forms. The more resonance forms.
That's what they had said was resonance forms. Like, do you know the different types? Because that would help.
The different types of resonance forms?
Yeah.
We're only going to deal with one type of resonance form. And those would be the equivalent resonance forms. There are some that you might think, let's see. This is well, let me just say one more thing about this. So this is why we like these structures, the condensed structures. CH3CH2OH. This is called the ethyl group. Sometimes it's written C2H5OH, and so that would be the ethyl group there. And this would be a CH3OCH3. So if we wrote the condensed structural formula, then we wouldn't get this mixed up. We're either talking about ethanol or dimethyl ether, one or the other. In Chem 1A, one of the challenging problems is this one, you know, N2O. N2O has a common name. This is dinitrogen monoxide. His common name is nitrous oxide. Or laughing gas. But what's the structure of this? So a lot of people will think this has like an ether-like, probably an ether-like structure with oxygen in the middle, because oxygen likes to bridge things like this. And then if we count the electrons here, there's 5 on nitrogen, it's 10, plus 6 on oxygen, so that's 16 valence electrons total. And so we could fill this out like this. And then, does that look good? So we complete the octet to the terminal, and then what we'll do is we'll try to complete the octet to the middle. But we ran out of electrons because this is 16 electrons now. And so we'll have to form a double bond. So this doesn't look good, so we'll go to this. And so if we take one of the lone pairs off nitrogen, we're going to have a structure like this. This one versus this one's better. We still don't have an octet, so this is still not good enough. And so we can complete the octet. There. Octet is done. And then you go, okay, that looks good. Every atom has an octet. And that looks good. But does that look good to you, or does it look a little odd? Yeah. Well, we skipped that. There's a little hint. It's not always correct. But the hint is that you want the least electronegative in the middle. But oxygen is in the middle of lots of things, you know. Like the alcohol is in the middle. There's a central atom yesterday. Well, what can it be a central atom here? It has a higher electronegativity, so we probably don't want to put it in the middle, but it was in the middle of dimethyl ether. So if it's in the middle of dimethyl ether, and dimethyl ether is a common chemical, you can buy this stuff. It's a liquid. You can buy it by a liter if you want. This is it here. Dimethyl ether is an organic compound. It's the simplest ether. Oh, sorry, it's a gas. Useful precursor to other organic compounds. Diethyl ether is a liquid. Lots of applications. Laboratory reagent and solvent. Ethers are this. Do you see this pictogram here? You gotta watch out. Ethers were used in the manufacture of illegal drugs and legal drugs, right? But some of these illegal drug labs, they'd let the ether leak out. And the ether vapor is actually more dense than air. So it would sink to the floor. And if there was a spark or a hot surface that ignites the ether, then the ether fires burn from the floor up. And so if you're engulfed in an ether fire, it's very, very bad. So all organic chemists worry about ether fires, and they worry about ether. You know, other vapors will rise to the top. They can get sucked out the hood or whatever vent you might have on the ceiling. But ether fires are very dangerous because of this. But,
isn't it like a anesthesia?
Yeah.
Yeah, it's so interesting. I saw on Pawn Stars, someone had like a vampire set from like 1800s, and it had like a, like not silver bullet, but just like the different things to fight against a vampire.
Oh,
And there was a bottle of ether.
was there?
Yeah.
Oh, ether's the what do they use that like in, what do they say they like it they soak a cloth in ether and then come up behind you and then place it over your mouth and
Yeah.
nose and then you get knocked out. It's one of those knockout things. Um, yeah, ether has been used as and I think it's still used in anesthesiology, not dimethyl ether, diethyl ether. Let's see. Well, anyway, there's a whole bunch of stuff. But the point is, though, you see, look at the fire rating. You know what's the worst fire rating? 4. Dimethyl ether is pretty bad. Ethyl alcohol is a 3. Acetone is a 3. Acetone is nail polish from over here. The blue one's hell. The yellow one's reactivity. This white one's special warning. This is NFPA, National Fire Protection Association, diamond. So here we have a bridging oxygen. Okay. But one of the things that should stand out as unusual is oxygen likes to form how many bonds? 2. And so this has how many? 4. This has 4 bonds. 2 double bonds counts as like 4 bonds. A double and a double. And it really is 2 separate bonds. 2 bonds because each double, but a double has twice as many electrons. So we want to look for octet, and then we want to look for what? Formal charge. And here's where the formal charges are weird. What would the formal charges be? So let's count it out. 1, 2, 3, 4, 5, 6 for nitrogen. 6 is minus, yeah. And then 1, 2, 3, 4 plus 2. And then 1, 2, 3, 4, 5, 6 minus 1. So the 2 nitrogens took an electron from oxygen. You think that's, if there's a tug of war, who should win? Oxygen. And so this doesn't, and then this is kind of a high charge for oxygen plus 2, especially in a competition with nitrogen. And so we start to look for other skeletons that might work, and then we might try this one, NNO. It doesn't look as symmetric. It's nice, but maybe it's like this. Mm-hmm. And then we complete the octet to the more electronegative. What's more like the nitrogen or oxygen? Oxygen. So we're going to complete the octet to the oxygen first, before nitrogen. If we still have electrons, then we can complete the nitrogen's octet here. And so that uses up all 16 electrons right there. And so who's going to sacrifice to make a double bond? Nitrogen sacrifice. Okay, was that enough? All right, now will nitrogen do a double sacrifice, or will oxygen have to? So nitrogen's going to have to sacrifice one more time. And then oxygen doesn't sacrifice at all. Or maybe nitrogen says that it's oxygen's turn to sacrifice. Well, both of these have octets. So the octet rule's good here, octet rule's good here, but
Formal charge.
yeah, we'd look at the formal charge next and then see.
There's no lone pair on the first nitrogen.
Yeah, there's a lone pair missing here.
But you can double bond on both sides.
It's symmetric, but let's take a look at the formal charge. Let's count it. 1, 2, 3, 4, 5. It's 0 for this nitrogen. 1, 2, 3, 4 plus 1. 1, 2, 3, 4, 5, 6, 7 minus. Okay, then over here I have 1, 2, 3, 4, 5, 6 1, 2, 3, 4. 1, 2, 3, 4, 5, 6. 0. All right, and so in this case, the nitrogen either way is going to have a positive formal charge. The difference is this one, oxygen gets the extra electron. This one, nitrogen gets the extra electron. Which one do you think is more favorable? Yeah, it's more favorable. But, you know, how big is the electronegativity difference between oxygen and nitrogen? Really, not that big. Nitrogen is a 3.0, oxygen is a 3.5. And so nitrogen is not so weak. And so what happens is we end up with a resonance hybrid here. And we would do some calculations for this one, but it turns out the resonance hybrid is not, you know, normally when we do a hybrid, it's a 50-50. If we have two of these, we just do a 50-50 mix. But in this case, the resonance hybrid is more like 80% this structure and then 20% this structure. And so these are two, you know, because these don't have the same energy. When you look at carbonate, all the resonance structures look exactly the same. But here, it's a little bit different. And so there is potential for a hybrid that's biased towards this because this is the more favorable form.
So we can calculate the percentages based off of the.
Yeah, that would give you a rough percentage. The electronegativities, you have to be careful with electronegativities because the electronegativities that we use are Pauling's electronegativities. There's more sophisticated electronegativities out there. Pauling versus other electronegativity. Pauling's electronegativities are great because it's so simple. But that's their problem. They're too simple. Let's see if Wikipedia has it. And so they're great, they're simple, but they're too simple because they don't factor in other things that will impact the electronegativity. And that's how it's bonded. So these are the Pauling's electronegativities here. Then we have the Mulliken electronegativities. Mulliken electronegativities have a much bigger chart. And then we have the Allen electronegativities. And there are more parameters that you have to input in order to determine the electronegativity of the element, and it depends on the compound it's in. And so, you know, we're not going to, the easiest is just to use the quantum mechanics program, and then you can figure this out easily. In fact, if you do this with quantum mechanics, we don't get these structures. This type of bonding, using Lewis structures like this, we're not doing any math, we're not doing any physics for this. But if we did all the math and physics, what we end up with is the hybrid. And the hybrid is, it's not going to be quite a triple bond. It's going to be like a 2 2/3 bond. And this is not going to be a single bond. It's going to be like a 1 1/3 bond, or 1 1/5 bond, you know, and this might be 2 4/5 bond, you know, depending on how the split is here. And so using quantum mechanics, it's easy to calculate what this is because the program will do it for you. And what we want to know is we want to know how the electron cloud is distributed in here, you know, where the electrons are. You know, do we have 6 electrons concentrated in this region or 4 electrons concentrated in that region? Use quantum mechanics.
So both are correct?
Well, this was the favored one, so if you're going to draw one, this would be the best structure here. But if you start thinking about resonance and resonance hybrid, this could be a potential contributor. It's not going to be as favorable, but it's a resonance contributor. And when you go to organic chemistry, you're going to see lots of different resonance forms. And some of them aren't as stable as others. And so they have even names for certain resonance forms. And so in Chem 1A, we look at this also, but substituted. These are quantum mechanical calculations here. You do. The blue and red and green. Green represents neutral. You know, everything's kind of balanced as far as electron cloud goes. Red are areas of deficient electron cloud, and blue are areas of actually, sorry, I have that backwards because for batteries, red represents what? Charge, positive or negative? Positive. But for these are called electrostatic potential maps. These are the electron cloud distribution. For these, positive is not represented by red. Positive is represented by what color? Blue, and negative is represented by red. I still don't understand why they did it that way. Because, but anyway, so you can see areas of positive, negative charge. This is what you get from quantum mechanics. So when we look at benzene, we don't see extra concentration of electron cloud here, here, and here. When we look at benzene, that means the double bonding electrons must be distributed evenly or delocalized evenly in the ring, because this whole cloud looks very even, doesn't it? It's not like wavy where we have, you know, extra concentration of density. So we do resonance for these things. Yeah. And we do these funky resonance forms like this. This looks like pretty good here. But what they do is, you know, they drop this lone pair here, create a double bond here, and then they pop this double bond out and make a lone pair on this carbon, making what we call carbanion. This one's going to be a heck of a lot higher in energy than this. And so these would be like non-equivalent in terms of energy. You don't have to worry about that in Chem 4. In Chem 4, all we're going to do is equivalent resonance forms.
I get it now.
This would be like in Chem 1A, and this would be although this is in Chem 1A also. You know, in fact, I think something similar to this is in Chem 1A. Yeah.
Is that why the Chem students would write R next to?
Chem students write R because they don't want to write the rest of it. R just stands for the rest of it. You know, and I'd rather not write the rest of it. That one's going to take too much time, so it's the rest of the molecule, basically. And so we use R for that. Or R just represents, you know, in general, like an alcohol. Alcohol is ROH. Or R is just whatever. A chain of carbon atoms, you kind of.
So can we do that in here? So aspirin would form a resonance?
So you have to draw all these out in organic chemistry. And how many are there here? 1, 2, 3, 4, 5, 6, 7. Or actually, there are only 6 because this is the same as the first one here. And so there's 6 resonance forms. And then you figure out which ones are the most stable and which ones are the least stable depending on where the charge goes. And then you can see which one's going to be the more dominant. You know, this would be the most formal charges. All the other ones have formal charges. But some of these, depending on where you put the charge, is better than others. You can do all kinds of things. But what was that question again?
Aspirin would
Aspirin?
form resonance.
Aspirin could, because aspirin, there's always going to be resonance. Aspirin is the carboxylic acid. And so if we look at the structure for aspirin, when you deprotonate aspirin, that is, when you knock off the hydrogen, then this resonance forms. Well, here's aspirin. Well, this resonance forms with the benzene right here. And so they're just showing you the hybrid kind of thing, where the other resonance form would have the double bonds in alternate positions here in the ring. This is the way organic chemists write the structure. They don't draw the hydrogens. So there's a hydrogen here that's not drawn. They're just drawing the bonds to carbon and other atoms that are not hydrogen, like oxygen in this case. And so, so it's easy to determine how many hydrogens. There are in a particular structure. So here, carbon likes to form 4 bonds. So we have 3 bonds, 1 double bond, 1 single bond. So that means there must be 1 hydrogen here. That would be the 4th bond. Here, 1 hydrogen. So we can figure it out. Here, this carbon likes to form 4 bonds. There's a carbon at the end. There's only 1 bond, so there's going to be 3 hydrogens. Yeah. We don't draw the lone pairs either. The lone pairs take time to draw. So it takes time to draw out the hydrogens, it takes time to draw out the lone pairs, so we just don't draw them. But they know they're there, and they can figure out how many, just based on it. There's a bridging ion, there's got to be 2 lone pairs here, 2 lone pairs here. We can see this is trigonal planar here. These are all trigonal planar carbons, so this forms a flat ring. This would be bent, tetrahedral bent. This would be trigonal planar. Here, this one, but usually twisted so it's in the same plane. Yeah. So it looks like there's going to be some interference between these 2 oxygens. The 2 oxygens are going to be negative, so we probably twist it so the oxygens on the opposite side, like this, rather than close to that. And then this is tetrahedral. Yeah, but there would be resonance forms. There would be more resonance forms if we did this. If we knock off the hydrogen off here, then that gives a negative charge there, and then we have the double bond on either of these. So there'd be 1 more resonance form for the deprotonated. Deprotonated means you have an acid. This is the acid proton. This is not an acidic proton. These protons here, these hydrogens here, are bonded to carbon. So those are non-acidic. These hydrogens here are bonded to carbon. Those are non-acidic. So we only have 1 acidic hydrogen here, which would be on the carboxylic acid. That's a carboxylic acid there. It's a carboxylic acid. Here, it's this is what we call an aromatic. Aromatic has these alternating, alternating double, single, double, single, double, single. When you see that alternating double, single, that's what we call aromatic. And there's lots of resonance forms you can draw for aromatic, because once we knock off that proton, then you make the double bond here, or elsewhere. This is what we call an ester. Like banana, the smell of bananas and the smell of fruits come from esters. Esters have pleasant odors. Carboxylic acids have unpleasant odor. When like butter goes rancid, it makes a carboxylic acid. And acetic acid. And then in your stomach, you have butyric acid. Butyric acid gives, vomit, its characteristic foul odor.
You also have hydrochloric acid.
You have hydrochloric acid too. And so, you want to get good at Lewis structures. So how many resonance forms?
I think is aspirin the one that comes from tree bark?
Originally, the aspirin that came from tree bark was like the dicarboxylic acid. The aspirin that came from tree bark had hydrogen here instead of a methyl group. And so it was too acidic and too harsh on the stomach. And so some chemists, what they did was they took the aspirin from the tree bark and modified it and made it less harsh on the stomach. It's still harsh. By what they did was they switched it from a proton to a methyl, hydrogen to methyl. So they just methyl group there instead, and that made it a lot better version of aspirin. So the original version of aspirin from the bark of, I think, the willow tree, it still works. You know, people chew on willow bark for pain, but this is much better. A lot of people take baby aspirin. Including me, I take baby aspirin. But, you know, there's a lot of controversy about that. You know, a lot of people are telling, oh, don't take it. I take it because I need my blood thinner a little bit. But apparently has other benefits in preventing blood vessel formation and viruses or that kind of thing, other things. So there are benefits towards cancer, I guess. Okay. Yeah, the willow tree. Heart attack and stroke, cancer prevention, dementia. This is what my memory is going to. Okay, other questions? How's that nomenclature?
Oxalic acid got me.
Oxalic acid, I'm with you, dude.
I'm pretty sure I wrote, I wrote chromate for rats. So I put chromic acid or whatever it was.
Well, it's only one problem, but oxalic acid is an important acid in titrations, so you should know. In Chem 1A, you use oxalic acid monohydrate as the primary standard. So it's a very common acid in titration, but not so common in Chem 1A. Oxalic acid precipitates, you know, calcium oxalate, so it's poisonous. It creates like the stones, calcium oxalate stones. Yeah.
Curious about the oxalate, like, where is that manufactured? Because there's no oxygen. It's just, or,
Yeah, it's one of the aids that you have to memorize. It's not on the periodic table or anything.
I guess the rest of them kind of like,
Yeah, the rest of
like, makes sense because they're like the element, the first element, like chromate or whatever.
mhm.
Chromium.
Right. Those make sense, but there's actually a lot of acids. Like this. Salicylic acid. You heard of salicylic acid?
Yeah.
Salicylic acid is aspirin. Acetylsalicylic acid is that variation of aspirin. And so when we have an acid like this, and we take off the acidic hydrogen here, This is acetyl. This is acetyl group here. This is acetyl salicylic acid. This is nomenclature for this is something that will pop up a lot more in Chem 1A. There are going to be a lot of acids that you've never heard of. And they're going to ask you things like, what's the conjugate base of that acid? We'll talk about conjugate bases later. Or what's, what forms. So if I neutralize acetylsalicylic acid, what forms? So let's go with acetylsalicylic acid plus sodium hydroxide. Sometimes when the formula gets kind of big, we just write out the name of this, or we'll just call it H. HA. A is the anion. H is the cation. This is the generic. And so you'll have stoichiometry problems like this. You'll get acetylsalicylic acid plus sodium hydroxide. But what forms? So what you'd have to first recognize is it a monoprotic acid, diprotic acid, triprotic acid? And then you'd know that acetylsalicylic acid is monoprotic. And so what you're going to form is you're going to form the salt of acetylsalicylic acid. What is the salt of acetylsalicylic acid? It's sodium acetyl
Acetylsalicylate or salicylate.
Yeah, salicylate. The 8 ending there. Sodium acetylsalicylate and water. And so we'll just call this NaA. So this is HA plus NaOH yields NaA plus H2O. So when you look at the generic equation, it's simple, but if you throw this, it's still simple, but this totally throws people off and they end up leaving the problem blank because they've never heard this acid before. But if you just treat it like a generic acid, then they're all right. That's kind of like the advanced problem. Like it throws off a lot of people. They don't know what to do. They leave the problem blank, and then some people get it. The answer. So that happens. And so oxalic acid is one of those. And so the way I had you memorize it is I had you memorize certain eights that like chromate, dichromate, permanganate, oxalate. Oxalate was this one, C2O4 2-. So that's going to make oxalic acid. Or we could go the other way, like the book does. Go from oxalic acid, memorize that, and then figure out what oxalate is.
I guess I'm just wondering why it doesn't, is it similar to carbonate or CO?
Yeah, it's.
I memorized it just because I don't understand why it's named like that.
Yeah, the origin of the name.
Because there's carbonate makes sense.
Yeah, carbonate like this. I don't know where the origin of the name is, but structurally it's very similar to carbonate. In certain respects. Because carbonate forms carbonic acid. Carbonic acid is weird in the sense that it is like a carboxylic acid here, but it has two of these. Oxalate or oxalic acid is very similar to this, except it has this. I didn't post that video, but these are ways that help you remember things. So if you know, rather than just memorize this outright, you know, oxalate versus carbonate, you think about the structure. And structurally, these are very similar. This is kind of a carboxylic acid that's kind of mirrored. This is like two carboxylic acids stuck back to back. The origin of the name, I don't know. And so this is like what the person on YouTube did. They took it a step beyond what I did for studying. You know, what I did is I didn't really care. I didn't have to have it like there didn't need to be any significance, you know, for a particular topic. But I always made a little story. And so when I had something in my notes that was hard to remember, I made a little story up as an annotation and just remembered that. And so this is how I would have remembered it. You know, and this is why I would have gotten it C2O4, you know, 2 minus or H2C2O4 versus H2CO3. But this is what makes it hard. The same thing, it makes organic chemistry hard because initially you have to do a lot of memorization. But once you start looking at the structures and the chemistry, then you don't have to do as much memorization. And so first, I think what kills a lot of people is the nomenclature. You know, nomenclature is tough, a lot of memorization. But once you're past that, then it becomes a lot easier.
Can we go over C3H7OH? The Lewis structure for that?
C3H7OH?
Yeah.
Okay, the way this is written is as an alcohol. This is your R here. This is your OH. And so ROH. The R group here, this is what we call a propyl group, I think. We can try it. Prop is 3 carbons, but there are different ways we can do 3 carbons. There's N, which N stands for the normal. The normal way. The normal way is 3 carbons in a chain. And then how many hydrogens would we need? We need 3 for this, 2 for this, and 2 for this. So that would be CH3, CH2, CH2, and then throw on the OH there. This would be called N-propyl alcohol. But there's one other way, you know, that we could do, and that's isopropyl. Isopropyl is going to have a little fishtail. So we throw in 1 carbon there, and then we'll throw in one side of the fishtail, this methyl, and the other side, fishtail. So it has this fishtail group here, and then the OH. But carbon likes to form how many bonds? 4. So we need 1 more bond to this carbon. This would be a tetrahedral, and so that would be it. So this takes care of 1, 2, 3, 4, 5, 6, 7 hydrogens. And so what we have is we have N-propyl alcohol, and we have isopropyl alcohol. Isopropyl alcohol has a common name. Well, actually, lots of people call it rubbing alcohol, and lots of people call it isopropyl alcohol.
See, so the way I had it like that, I thought was correct, but the book has it where the oxygen is through the carbon, not in the middle. So after the third carbon, instead of where the hydrogen is, there's an oxygen and then there's a hydrogen connected. Let me show you. You see what I mean? That's how the book has it.
Okay. Remember what I said about this? What are the angles here in tetrahedral? 109.5. When you have a tetrahedron, and this is why in organic chemistry, you're not allowed the models on exams. So what people do is they bring extra pencils on the test, and then they make a tetrahedral structure like this, and then they ask themselves this. Okay, let's say the purple is the oxygen, as I've drawn it here. But you have to remember, there's free rotation about single bonds. So if I just rotate this single bond here, the purple is here right now, but if I rotate this, the purple is down. So I could just rotate this down. And so what they have drawn there is the exact same structure. I'm going to just do condense CH3CH2, then C. This is the exact same structure. All they're doing is they're just rotating it. They can just rotate this because the way this is, you have to look at this three-dimensionally. When you look at this three-dimensionally, what we have here is this. We have a carbon here, and then it's going to be like a propeller here. The Lewis structure doesn't have to match anything here. So right now I have the Lewis structure drawn kind of like this. The two lone pairs this has to be bent. It's not linear. And so I have something like this. Well, all I do is rotate this propeller and then put the oxygen down and then rotate the hydrogen. This is like a propeller too, and rotate the hydrogen down. And so I get this exact same thing. If I wedge this down now and kink that up, it would end up with a structure like this. So in organic chemistry, you immediately recognize those are the two exact same structures. Because you've built so many of these models and you played with the models and you see how they work that you'd say, okay, these are the same thing. There's no difference. Does that make sense?
Yeah.
Whereas these two are not the same structure. In fact, isopropyl alcohol has a systematic name. We call this one, these are the common names. This one's called 1-propanol. This one's called 2-propanol. There's no such thing as 3-propanol though. And 2-propanol can be drawn like this. You see these two are exactly the same structure? Yeah, these two are exactly the same structure. And the way we do organic chemistry is we number the carbons. And so this is called 1-propanol because we're going to call that carbon 1. Or we could call it carbon 3. So if we numbered it left to right, 1, 2, 3, then this would be 3-propanol. But what we try to do in organic chemistry is keep the number small, as small as possible. So if you could call this 3-propanol or 1-propanol, it's best to go with 1-propanol. And so there's no such thing as 3-propanol. So with 1-propanol, but when we look at this one, we just pick one of these carbons. That's carbon 1, this is carbon 2. So this is called 2-propanol because it's on carbon 2 rather than on carbon 1. Carbon 2 is stuck in the middle of this particular structure. The 2-propanol is the same thing as isopropyl alcohol, which is the same thing as rubbing alcohol, etc. And you learn all how to name all these things in organic chemistry.
Is there a hydrogen missing from that one?
Yes. There's a hydrogen missing here. That's good. You automatically see there's something missing on that carbon. It doesn't have an octet. Doesn't have the right number of hydrogens. The organic for Chem 4, I'm not going to test you on organic nomenclature. You know, the really common ones are methane, and maybe propane, butane. Methane's not that common.
Are you going to test this on isomers?
No. I'm not going to test you on isomers either. And so the organic is just because we work with organic chemicals, so you should have a little bit of knowledge. There are a lot of organic functional groups, and each set has their own set of nomenclature rules. Let's take a look at organic functional groups. I thought I might have shown this before. Images. There's some overlap. This isn't even all of them here. So we see the R here. It's very common. Let's see what they say. They have R footnote 1. I'll show it here. And so we did the alkane here. We looked at the alcohol here in the carboxylic acid. But you look at all these other structures, and then you see here, you know, they're still doing the expanded octet here. If you look at the sulfur, it's expanded in the sulfone. So we got 2 double bonds here. Same thing here. This is expanded octet. Expanded octet. Sulfur, you know, since it's third period, can expand. If you're in the third shell or the third period, third row in the periodic table, you can expand. So that's some functional groups here. All right, one of the biggest applications for Dalton's law is when we collect gases over water. Here, this is an experiment you're going to do in Chem 1A. You'll hold a burner and then just heat up some KClO3, which is white. And then they put this black powder in there, a little scoop of that. And then they heat this up to decompose it into oxygen. The oxygen, well, there's air in here first. And so what we're going to do is we're going to do Avogadro's law. And so we'll take the volume of the air plus the volume of the oxygen. They're going to just be additive. And so whatever extra volume I get will be the volume of oxygen. That's Avogadro. And then once I collect the oxygen up here, this will be, well, actually, first what's going to bubble in here is air and oxygen. But it doesn't matter because, you know, volumes are additive. So if I had 1 milliliter of air and I had 1 milliliter of oxygen, then I'm going to have 2 milliliters of gas. The volumes are additive when the pressure is constant. And so this is a bit of a pain because what we have to do is we have to get the pressure. over this. It's actually not. You get a room pressure. At the end, you got to get the pressure the same. And so here, the pressure is different than the air pressure out here. Originally, it was open to the air. So what we'll do is we'll do this. We're going to get a big sink, and then we're going to submerge this tube until the water level in the sink matches the water level of the gas inside the tube, and then we've done what's called equalized pressure. So once we equalize the pressure, then we know the total pressure of this gas here. We can measure the volume of the gas, and we can measure the temperature of the gas. And so something like that, we're measuring P total. P total is going to equal the pressure of the wet hydrogen, or not hydrogen, sorry, wet oxygen, which is equal to the pressure of the dry oxygen plus the pressure of the humidity, water. The humidity we can get from a table. And so at the end of this, we treat it as a Dalton's, as a constant volume. So the volume of the oxygen, in other words, the volume of the wet oxygen is equal to the volume of the dry oxygen, which is equal to the volume of the humidity, the water vapor. This is should be a G, not an L, sorry. And then what we can do is we can just figure it out because we want to figure out the moles of oxygen. The moles of oxygen will just equal the pressure of the dry oxygen times the volume of the dry oxygen divided by R and the temperature of the dry oxygen. Well, the pressure of the dry oxygen, we can just calculate. We just take the pressure of the wet oxygen and subtract the pressure of the humidity of the water vapor, and we get the pressure of the dry oxygen. The volume of the dry oxygen is the same as the volume of the wet oxygen, so we just measure the volume of the wet oxygen. And the temperature of the dry oxygen is going to be the same as the temperature of the wet oxygen. So, temperature of the dry oxygen is equal to the temperature of the wet oxygen. And so this is how we use this for calculations. We got to make sure we keep track of this. This is Dalton's. Dalton's is constant volume. Whereas if we did this using Avogadro's, then we would set things up differently. And so we just have to be aware of that. So here they show it here. So how do we measure the pressure total? What we do is we get the water level inside the tube to match the water level outside. So the pressure of the atmosphere is equal to the pressure of the gas, the wet gas. So once we equalize the pressures, then we know the pressure of the wet gas. And we can figure out the pressure of the dry tube. So that's what we're doing this. Figure. Here. So this is the biggest application of Dalton's that we'll probably be doing. All right, so now we're going to shift. So that was gas mixtures, Dalton's and Avogadro's. And so in 15.2, we're just looking at pure liquids. What are some properties? Well, one of the properties of water is it evaporates. That's what causes the humidity. This evaporation of water. So let's just look at some macroscopic properties. Gases may be compressed, but liquids cannot. Have you heard of hydraulics? Hydraulics operate because you can't compress the liquids. So they use liquids to push things around, that kind of thing. Your brakes are hydraulic systems. So you push on your brake pedal, then compresses the liquid, the brake fluid. However, if you ever get air in your brakes, you'll get what's called spongy pedal. You want a firm pedal because liquids can't be compressed. But if you have a spongy pedal, that typically means you have air in your brake line. And what they need to do is they need to do something called bleed the brakes. When they bleed the brakes, they try to get rid of all the air out of the line, so you get a firm pedal once again. Gases may be expanded, liquids cannot. Gases have low density, liquids have relatively high densities. Liquids, density of liquids are about 1,000 times more dense. You know what the densest liquid, what's the densest liquid you can think of?
Mercury.
Mercury. The density of mercury is really high. It's more dense than copper. You know, the density of mercury is like 13 grams, which is more dense than lead. So if you took a lead brick and throw it into a mercury pool, would it sink or would it float? It would float because lead's only 11 grams. And so lead brick would float in a pool of liquid mercury. In fact, you should be able to walk on mercury. So you wouldn't have to worry about drowning in a pool of mercury.
Going into physics, but buoyancy doesn't have a role in this.
No, buoyancy, you'll sink a little bit, you know. What you're going to do is you're going to displace your weight. So if you weigh, let's say, 100 pounds, then you're going to displace 100 pounds worth of liquid mercury. But 100 pounds worth of liquid mercury is very little. It doesn't take much to do that. So there's going to be buoyancy. Gases may be mixed in a fixed volume, liquids cannot. When you mix liquids, the volumes are additive, but they're not perfectly additive. Now, it depends on the liquid. So, for example, if you took 1 milliliter of ethanol, pure, and mix it with 1 milliliter of pure water, you'd expect 2 milliliters of ethanol solution. But sometimes you don't. You know, sometimes the way the molecules pack together in a liquid mixture isn't additive. We'll talk about that. Gases exert constant pressure on the walls and uniformly in all directions. Liquids don't. Liquid pressure increases with increasing depth. So the deeper you go, the heavier things weigh. Well, those, you really don't have to worry. Most of those are just what you visually have seen. What we're going to be looking at are these: vapor pressure, heat of vaporization, boiling point, viscosity. These properties depend on this thing called stick togetherness. The stick togetherness, these molecules are sticky. They'll stick on certain things. We call these attractive forces or intermolecular attractions. So stick togetherness is not really the term people use. Nobody uses it. Some people will use sticky, for the molecules. But we call them intermolecular attractions. So let's take a look at the first one of these, vapor pressure here. And what causes the humidity? If I just put liquid in here and this is dry air, this dry air pretty soon is going to be humid air because of the water. And humidity is going to result when some water molecules vaporize off the surface. And the water molecules are stuck together. It's not because of the weight. Water molecules don't weigh anything. It's because they're sticky. And that's what holds the water molecules together. And the weight, the whole thing of this whole collective thing is going to be held down by gravity. Here. If there was no gravity, you get blobs, like of water. They're stuck together, but but they'd be like on the space shuttle or something, or the space station, and they'd be floating around these blobs. And so what's holding them really are electrical forces. And so what we do is we have electric dipoles. Water molecules are polar. The oxygen's negative, the hydrogens are positive. And so the oxygens orient towards the hydrogens, and the hydrogens orient towards the oxygens, and there's electrical attraction there, Coulombic attraction or electrostatic force holding them together. And so that's what causes the water molecules to be sticky. And these dipoles are pretty big, and so the water molecules are fairly sticky. But even at room temperature, they'll vaporize. You know, as the temperature gets hotter and hotter, then the humidity will go up. Because as the temperature gets hotter and hotter, we'll just get more water molecules to vaporize. Okay? And so eventually, what we're going to do is we're going to have 100% relative humidity. When we have 100% relative humidity, the air here has been saturated with water vapor. Sometimes we won't. You know, we pop the lid off here, the core, and this whole thing might evaporate without ever saturating the gas. But when we use this, we always assume that this gas, the O2, has been completely saturated with water vapor. And then we can look it up in the table. You know, what is the pressure? It doesn't matter how big this is, you know, it just depends on the temperature. That's vaporization. Evaporation or vaporization. Okay, and so once this is saturated, then we can measure, you know, the pressure, and that's called the vapor pressure of water. So let's take a look at a table and see how the vapor pressure this is how it changes. It's nonlinear. So as the temperature goes up, the vapor pressure goes up, but in a nonlinear way. As the temperature gets pretty high, then it shoots up like this. This is called a vapor pressure curve. Yeah, it shoots up exponentially. So typical vapor pressure curves, it's nonlinear, it's exponential. Boom. Yeah. A curve is kind of a pain sometimes. A curve is good, but usually people just use the data table. This is all the data that they use to generate that curve. And so can you see the curve? It's hard to see the curve here, looking at the individual data points. But let's say our temperature is 25.0 degrees C. You just go here. At 25.0 degrees C, the vapor pressure is 23.576. The other thing is, what's best is not a curve, not a data table. What's best is a mathematical equation describing it. And so there's a mathematical equation that describes this curve. And so you can just plug in the temperature and it calculates the vapor pressure. Otherwise, if let's say our temperature were 24.95, you know, 24.95 would be halfway between 24.9 and 25.0. It's halfway, and so we assume it's halfway between these two, but it's not really halfway because it's a curve. You know, it's not a straight line. If it were a straight line, we do something called linear interpolation. Linear interpolation assumes it's linear. If the data points are really tightly spaced, then it's fairly linear. Like if I look at a small segment, it looks linear. You know, but if I look at a large segment, it's non-linear. Large segment of temperature. And so we would still use linear interpolation here because the data is fairly close to one another, so the error is going to be small. But if we had the equation, we wouldn't have to do that.
So the table will be the rate of change.
The rate of change is changing. The rate of change is the slope. And you can see the rate of change is kind of slow here. Not much is happening. And then when you get out here, the rate of change goes faster and faster and faster. You know, when the slope changes like that, You know what math is really useful for that kind of stuff? Yeah, calculus. Yeah, with calculus, you can get this pretty easily. You can figure out the rates of change and other stuff. Yeah. So these are all vapor pressure curves. And so the hotter the temperature, this is 100% saturated. And so we've saturated it. And so at higher temperatures is much more humid. So than at lower temperatures. We don't like high humidity. We don't like high humidity. Why? I mean, if it's really humid, like let's say if it were 100% humid, it'd feel really muggy, right? It'd feel really muggy because you can't, the air is already saturated with water. And so if let's say you're sweating or perspiring, that sweat's not going to evaporate. You know, if it doesn't evaporate, then there's a problem. And we need it to evaporate because that's one of the ways the body regulates heat. It's by heat of vaporization. So if we could vaporize it, it cools us down because vaporizing the water takes energy. You know, it takes energy to vaporize. And so if we have net vaporization, we'll cool down because that's going to require heat to evaporate the water. But the problem is once it's saturated, what we have are two processes occurring. You see the arrow going up off the surface, that's called evaporation or vaporization. So we have evaporation, vaporization, vaporization here. You see the arrows coming down? The arrows coming down means a water molecule comes down and hits the surface. Two things that can happen. One, it can bounce off, or two, it can get stuck. Since water molecules are sticky, it gets stuck. That's called condensation. So we have 100% humidity. What it means is this, that the evaporation of the vaporization rate is equal to the condensation rate. So if 3 molecules vaporize, 3 molecules condense when it's saturated. When the air is not saturated, we'll have net vaporization. That is, maybe we'll have 3 molecules evaporate, but only 2 condense. You can lose some heat. The reason that happens is, let me show you. Yeah, we get a figure for that. That's called reaching a dynamic equilibrium. So let me show you a figure, not from our book, that vapor pressure So when we have a liquid like this in a closed container, let's say this is dry initially, dry air. What we're going to have is we're going to have net vaporization. There's no water molecules here to condense, but we have net vaporization. And then over time, what's going to happen is we're going to have more and more water molecules in the air. And so once you start building up water molecules in the air, then some of these can condense. Some of these will vaporize. But the vaporization rate, that is, let's say for every 2 molecules that vaporize, only have 1 that condense. But what's going to happen is the concentration of the water molecules in the air is going to get high enough that eventually it's going to match. And when it matches, then what we have is saturated the air, or we have wet air now. And so what that means is that the concentration is high enough, so for everyone, vaporization never stops. So let's say I vaporize 3 of these, I'm going to condense 3. And so the water molecules are constantly vaporizing and constantly condensing, but we have no net condensation, no net vaporization. And so the concentration of water molecules in the air is fixed. And then we call this 100% relative humidity. If I cool down the temperature, then that's going to slow down the vaporization. And that'll lower the humidity. If I warm up the temperature, then that's going to increase the vaporization, which will make things more humid. So 100% relative humidity is not a fixed number. It depends on temperature. And we just look it up on a vapor pressure table or vapor pressure graph, or plug it into the vapor pressure equation.
So, why does carbon dioxide evaporate faster than water?
Carbon dioxide?
Yeah.
Carbon dioxide, you look at the boiling points or the melting points or whatever. So carbon dioxide is normally a gas at room temperature, whereas water is normally a liquid at room temperature. And so carbon dioxide is already boiled off into a gas. It's just a gas that's stuck inside the liquid. And so it's going to come out first. This is the principle of distillation. You're going to distill the most volatile substances. Volatile substances have high vapor pressure. And volatility. So volatile have high vapor pressure. So water, its vapor pressure is not so high, but if this were alcohol, ethanol is much more volatile than water. It vaporizes much more easily. Or if this were like syrup is pretty non-volatile. Syrup has a hard time vaporizing. And so it wouldn't generate much pressure. So it depends on the strength of intermolecular forces, traction.
I was going to say, remember an episode about field matters well, where they were distillating salt water, like first boiling the plastic part, so all the water condense on top.
Yeah. Yeah. That's I've seen that, like if you're stuck in the desert or something, you want to use the sunlight to vaporize the water and then capture it on a tarp, like this, cool tarp or something, yeah. Survival. That would be distillation and vaporization. That's pretty cool. You know, there was that probe that went to the comet, that landed on the comet, you know, and the comet tail is like when the sun hits it and it starts to vaporize these things. These things are somewhat volatile versus asteroids. You know, do you see a tail on an asteroid? And so they set the probe on the comet, and do you know what they found? One of the things they found on the comet? This surprised me. Rosetta, this comet here, which is this kind of this hourglass-shaped comet, they put a probe here, and you know what they detected? Glycine. Glycine is an amino acid, so they found an amino acid on the probe. not the probe, on the comet, which is pretty interesting. Because I wouldn't have thought you'd have glycine. Amino acids are important building blocks for proteins. Proteins are made up of amino acids, glycine being one of them. Anyway, that was the Rosetta comet, and this is just recent data. There's a YouTube video about this. Very interesting. Well, glycine's fairly volatile. You expect it to, fairly volatile compared to rock. The rock isn't so volatile. So it's interesting that the glycine is involved and vaporized off the surface of this. Or maybe there's glycine deeper in there. It makes you wonder what other molecules. They found a lot of organic molecules on this. I think they found something like 50 different ones.
Yeah, there was, I don't know if it was a meteor or what, but they estimated it had like so many grams of gold and silver.
Oh, yeah.
And if we were to somehow extract it, it'd just ruin the world's economy.
Yeah.
I know there's like two of them, and one of them has a lot of platinum, and one of them has a lot of uranium. I forgot what medium, but
Yeah. Well, I wonder what would happen to the price of gold if it became very common.
Yeah.
I can't remember. There's a book I read about this. They found some diamond mine in a volcano or something like that, and they lived there. Do you recall this story? And it's this like ultra wealthy family, and what they do is they just leak some diamonds out from their mine a little bit at a time because they don't want to flood the market with diamonds. Otherwise, the price would just go way down. But they have this enormous. And when I was a geology student, there's a guy there who was also a student, and that was his goal was to find deposits, gold deposits, diamond deposits, and what he was going to do is he's going to go make a claim and then just live off the diamonds or gold. I wonder what became of him. I'm not sure if he ever found it or not, but it's one of those things that would be pretty cool.
so kind of like the movie from you watched the movie Blood Diamond?
What, Blood Diamond?
Yeah.
No, I haven't watched that.
It's a movie where the characters explain like the diamond industry in Africa. I forgot what company it is.
Mm-hmm.
But they hold most of the world diamonds and like they keep on reserve so prices go up or down.
Yeah, and the funny thing is you can make diamonds in the laboratory. So if you can make diamonds in the laboratory, are they so valuable anymore? The synthetic diamonds are very common. Synthetic diamonds, diamond films, lots of diamond applications for diamonds. But they're still valuable because, the authentic diamonds have defects in them and are not perfect like the lab synthesized ones. So, a gemologist can tell the difference. Another interesting thing was phosphorus. So these are like the building blocks of life. And water too. Hydrogen and oxygen, there's a lot of hydrogen and oxygen on the comets compared to hydrogen and oxygen on asteroids. And so one of the hypotheses was that the water on Earth came from comets. But they're thinking that's less likely. The water on Earth, they're thinking, came from asteroids. Even though asteroids barely have any. Let's take a break now and then. So it goes from a very small volume, from ammonium nitrate, the solid doesn't take up much space, to a very large volume. If this were under normal conditions, we'd go from a tiny volume to about 25 liters plus 25 plus 25. We'd go to a volume of 75 liters, 3 moles of gas would be about 75 liters. Considering mole volume. Maybe we're close to room temperature. But this is way above room temperature, 427, 396. But you have to recognize that all the nitrous oxide, N2O, and all the water, gaseous water, came from ammonium nitrate. And the stoichiometry holds.
Under 1410, can you go there?
Yeah. 1410.
Yeah, this is the active learning example.
In section 1410,
Yeah, I think.
do you know what page that's on?
Oh, hold on, let me try it. Let me pull it up again. Yeah, it's the active example 14.13, gas stoichiometry ideal gas equation method.
This one's tricky because they don't give you the states here.
Oh, not that one.
All right.
It's page 536 on my book. Up there.
This one?
Yeah.
Okay.
So I was trying to do that in reverse because there it's asking for how many liters and we want grams, so I was trying to.
Yeah, we did an example of this as a homework problem earlier, but this one's easy because it only forms one gas, CO2. They're asking you how many liters of CO2 or how many liters of butane. How many liters of CO2? So there's only one product here.
Okay.
Well, this one's going to be more difficult because what we end up with is with a gas mixture. So let me look at it like this. So first off, we just have solid ammonium nitrate. And it's going to take up maybe this much volume here. And then we heat this up. And it can decompose into a lot of different things. But one thing it's going to decompose into could be nitrous oxide, amongst others. In this case, we're only going to form nitrous oxide. So this is going to decompose into nitrous oxide gas, H2O gas, and H2O gas. And because of the stoichiometry of this, we're going to have one N2O and two H2Os. And so what we have is this. It's going to be, how many liters was this? 82.3. And what was the temperature?
447 Celsius.
So we have this. So the other ways of solving this are this. All the nitrous oxide, all the water comes from ammonium nitrate. So it has to be formed in a 1-to-2 ratio. There's no water from humidity or anything else that could screw up this 1-to-2 ratio. And so as long as we have this 1-to-2 ratio, then we know this. We have something called the mole fraction. The mole fraction is always valid. So the mole fraction is always valid. That means, what's the mole fraction of N2O? And so the mole fraction of N2O is we have 1 mole of N2O for a total 3 moles of gas. And the mole fraction of H2O is 2 moles of H2O for every 3 moles of gas. And these two have to add up to 100%, or 1 over 1. So 1/3 plus 2/3 gives us 3/3, or 100%. Or we can do this in terms of mole percentage. In terms of mole percentage, this would be 1/3 is 33%, 2/3 is 67%. So 33% N2O, 67% H2O gas. All right, I didn't give you this equation last time, but this is an equation that you learn in Chem 1A. The mole fraction of the gas is this, is the number of moles of that gas, the gas in this case, over the total number of moles. And so this is the mole fraction or mole percent if we want to convert it into a percentage, we just multiply by 100. This is equivalent to the volume fraction, and that is the volume of A over V total. This is under constant pressure conditions. So this is Avogadro's. Avogadro's is valid only under constant pressure. If it's not under constant pressure, then it's not valid. Okay, which is equal to the pressure fraction, PA over P total. So the mole fraction is equal to the volume fraction, which is equal to the pressure fraction, but they can't be equal. All three cannot be equal simultaneously. And so we can have the mole fraction valid and the volume fraction valid. The pressure is constant. Or we can have the mole fraction valid and the pressure fraction valid if we're under constant volume. So if we can pick one of these, like say, if I want to figure out how many moles of N2O I have in there, then I could do that here. Okay, so there are two things. Was the pressure given? What was the pressure?
896 torr.
896 torr. So this is P total. This is V total. And this is T here. Okay, so the way I could do this is this. We could figure out the total moles of gas and then use this to get the moles of N2O or the moles of H2O or the moles of ammonium nitrate. Because the balanced chemical equation is just the mole ratio. Okay, or I could do volume. If I do a volume fraction, then what I say is that, well, N2O is 1/3 of the total, therefore the volume of N2O will be 1/3 of the total volume. Does that make sense? And so if I want the moles of N2O, then I would do this. I would, the moles of N2O is equal to the pressure of the N2O times the volume of the N2O divided by R, temperature of the N2O. Now, the pressure of the N2O is, well, this is Avogadro's, and therefore everything has to be under the same pressure, constant pressure. So the pressure of the N2O is just going to equal 896 torr. That is, the pressure of the N2O is equal to P total, which is equal to P of the H2O. And so the pressure here I'm going to put in is 896 torr, and then we're going to convert that into atmospheres. 1 atmosphere is equivalent to 760 torr. However, the volume, is the volume going to be 82.3 liters? No, what is the volume going to be? It's going to be 1/3 because the volume fraction should be 1/3. So it's going to be 1/3 of, in other words, we could do it like this. If I want to use dimensional analysis, it would be this is in liters. So 1 liter of N2O for every 3 liters total gas. This is what we call the volume fraction. Times the total volume will give us the volume. So it's 1/3 of 82.3 liters total. And so the liters total cancels out the liters total, and that leaves me with liters of N2O gas. And so now I have pressure times the volume divided by RT. So this is R, and then the temperature is the same, and the temperature doesn't change. So this is if I want to use the volume fraction to solve this problem. But I can also solve this problem using the pressure fraction instead. Because there are 2 ways of looking at gas mixtures, actually 3 ways, mole fraction, volume fraction, pressure fraction. Okay, look at the difference here. If I solve this using not Avogadro, what did I call this one? Pressure fraction or partial pressures is Dalton's. So if I solve this using Dalton's, it's different. The equation is the same. The moles of N2O will equal the pressure of the N2O times the volume of the N2O divided by R, temperature of the N2O. And so what's going to be different is this. Is the total pressure here 896 torr, the pressure that's exerted by the N2O? No. And so we're going to have a pressure fraction here. In fact, maybe what I'll do is I'll convert it into atmospheres or I'll leave it as torr. It doesn't really matter. That is, I'll do the pressure fraction here and then convert it. And so what is the pressure fraction? The pressure fraction is that what I'm going to have for 1 torr that's going to be generated by the N2O for every 3 torrs total that's going to be generated. And so if I have 3 collisions, then one of those collisions will be N2O, and that's going to generate the pressure of the N2O. And so I'm going to multiply this by 896 torr, and then convert this into atmospheres. 1 atmosphere for every 760 torr. Okay, what would the volume of N2O be? The volume of N2O is going to be Is it going to be 1/3 times 82.3? Yeah, it's going to be the entire thing. And so here, when we do it this way, the volume of N2O is equal to the volume total, which is equal to the volume of the H2O. It's because it's constant volume. And so everything is going to have the same volume. That is 82.3 liters. So this is going to be times 82.3 liters divided by R times temperature of the N2O, which is going to be the same for both. So, in other words, for Avogadros, I take the fraction of the volume, and the pressure is the same for everything. I can do the exact same problem, I'll get the exact same number, it's just a different way of looking at the mixture. If I look at it based on Dalton's, I'll take a fraction of the pressure, and the volumes are all the same. Do you see that? And so here, the volume fraction, here, the pressure fraction, the number comes out the same. So these are 3 ways of looking at this. And so sometimes we have to calculate, how much N2O is generated in this mixture, or how many moles of N2O do I have when I'm given the total here. The problem is this. The problem is some people will take 1/3 of the volume and 1/3 of the pressure, thinking that N2O makes 1/3 of the mixture, and they think that they can take 1/3 of both. But you see, you can't do that. This is, even Chem 1A students have a hard time with this, so don't worry if this doesn't quite click. Because the problems aren't going to be this hard. Chem 4. Well, anyway, look at collective, or do you want some more time? Yeah. Is that something where you want to think about these things?
Can you,
Oh, yeah. Go back to chapter 15. So vapor pressure the more sticky the molecules or the particles are, the lower the vapor pressure, the less sticky the higher the vapor pressure. And the stickiness is called the intermolecular attractions. And so you need to know this trend. As the molecules become more sticky, then they become less volatile. And that's going, if they're less volatile, then they're not going to vaporize so easily. And that's going to result in a lower vapor pressure. And vice versa, the less sticky they are, the greater the vapor pressure. Okay, the next thing we have is heat of vaporization. Heat of vaporization is the amount of energy it takes to vaporize it. And so we could see this. This is called an energy level diagram here. And so the liquid is lower in energy than the vapor. So as we go up, we're going up in energy. So this arrow going up is going to cost us energy. We're climbing in energy here, and we give delta H as the symbol, and we call this delta H of vaporization. It's endothermic, because we're going up in energy, it has to absorb energy. However, the reverse process is exothermic, and it's exothermic by the exact same amount. And so if you consume energy here, vaporizing one molecule, and you condense it, then you're going to be net zero energy. Because they're equal and opposite. And so normally we give a positive for the delta H of vaporization, a negative for this. But what we want to know is how it varies. And so delta H of vaporization is the molecules become more sticky, they become harder to vaporize, and becoming harder to vaporize requires more energy to vaporize it. And so we have increasing delta H of vaporization. And the opposite of that, condensation, would be increased as well. We have boiling point here. And so the stronger the intermolecular attractions, the harder it is to boil. That is, we're going to have to increase this. We have something called the normal boiling point. The normal boiling point is when the vapor pressure equals the barometric pressure, or the atmospheric pressure. And then we have boiling occur. And so here you can see this liquid boiling here. And so the vapor pressure caused by the liquid vaporizing, when it matches the atmospheric pressure or barometric pressure pushing down, then we have boiling. Boiling occurs when we get spontaneous vaporization here. The normal boiling point is the barometric pressure is 1 atmosphere. This is what we call normal. However, 1 atmosphere is normal atmospheric pressure at sea level. If you go up in elevation, then the atmospheric pressure goes down. And so here you could see this. This has some other stuff in here, but this is the vapor pressure curve. And we can see the vapor pressure curve increases exponentially. And when we hit 100 degrees C, the vapor pressure equals, this is in bar, it's slightly above, equals 1 atmosphere there. And so this is normal. This is normal atmospheric pressure. Therefore, the normal boiling point is 100 degrees C. However, if you're at high altitude, water boils at a colder temperature because atmospheric pressure is lower. So if you're in Denver, the atmospheric pressure is lower, the weight of the atmosphere just weighs less, you don't have as much. And therefore the boiling point of water is lower. And if the boiling point of water is lower, it's going to take longer to cook things. And so they have high altitude. Have you seen high altitude cooking instructions? You have to cook it longer, basically. So, for example, if you're on Everest, if you're at the summit of Everest, at the summit of Everest, we have about 1/3 of an atmosphere. 1/3 of an atmosphere would be about here, which would place it around 70 degrees C, and 65, 70 degrees C. Have you ever tried to boil pasta when the water's not boiling? Like say it's a little cooler than boiling. Have you ever tried cooking pasta at room temperature? It doesn't work, right? It would take forever. It would take forever because the room temperature is only 25 degrees C. So the colder the temperature, the longer the cooking time. In fact, there's a rule of thumb that I learned when I was taking Chem 4. And the rule of thumb is for every 10 degrees C temperature increase or decrease, it changes the cooking time by about twofold. So this is why they're pressure cookers. Pressure cookers, they want to get the temperature even hotter, than 100. 100 is a max for water unless it's in a pressure cooker. If you put it in a pressure cooker, you can go above 100. You can go above 100 because the water's not going to boil because you're keeping it under tight or high pressure until the vessel explodes or something. But basically, if you cook things at hotter temperature, they cook much faster. So pressure cookers are good in that way. You wouldn't want a low pressure cooker unless you want to cook things slowly. But we have the normal boiling point versus the boiling point. The boiling point is just when P vapor is equal to the barometric pressure, whatever the barometric pressure is. And the barometric pressure varies depending on where you are. And therefore the boiling point varies depending on where you are. Okay, the next property is viscosity. So the stronger the intermolecular attractions, the higher the viscosity. Viscosity is resistance to flow. So if we have high viscosity, it doesn't flow very easily. That is, it's harder to pour. If you have low viscosity, it's very easy to pour. And so this is like trying to pour maple syrup. pours slowly because it has high viscosity. Or honey has high viscosity, it pours slowly. Now, that's because we have strong intermolecular attractions there. It's going to prevent it from moving much. Then we have surface tension. Surface tension is to break the surface of a liquid. So viscosity, and then we have surface tension. So there are some things that should sink. One demo of surface tension is if you have water. Have you ever tried to float a paperclip on the surface of water?
Yes.
Yeah. You can float paperclips on the surface of water. Paperclips have a pretty high density, like maybe about 8 times that of water iron. Yet they don't sink. It depends on how you float it. So you can take some tweezers and try it. But that's surface tension. What's preventing it from sinking is breaking the surface water. In order for that paperclip to sink, we have to break the water molecules apart. But if the water molecules are really sticky, then they get stuck together. And so the floating paperclip trick. Let's see. So this is what's being shown here. Vapor pressure, vaporization, normal boiling point, and intermolecular attraction. So if we have strong intermolecular attractions, then we expect low vapor pressure, high heat of vaporization, and high boiling point. If we have weak intermolecular attractions, then we expect high vapor pressure and low heat of vaporization and low boiling point. You don't need to know the numbers, you just need to know the trend. This is surface tension here. When we're dealing with surface tension, also vaporization, whatever else, we have things that are called interior molecules or bulk molecules versus surface molecules. Surface molecules are less stable. Interior molecules are more stable. Interior molecules are more stable because they have a full 360 spherical attractions, spherical distribution of attractions, versus surface molecules are only attracted to molecules underneath it and to the sides. There's nothing holding it in other than these molecules here, whereas the interior ones are being held strongly by all the other molecules. And so when you break the surface, you're creating more surface molecules. When you create more surface molecules, it's higher in energy, it's less favorable. So we're going up in energy. That's basically the trends here. Here's an insect walking on the water. Surface tension of water creates a difficult to penetrate skin that will support small bugs or thin pieces of dense metal, such as needle or razor blade or paperclip. The bug literally runs on the water, does not float in it. But other people are saying there's more to it than surface tension. And so there are people studying the legs, the feet of these bugs to see how they interact with water. And it turns out that some of these, like ducks, ducks have what's like a hydrophobic coating on their wings, which repels water, which makes it more buoyant. And so the same thing here with the bugs. So it could be more to it than just surface tension. Right, but the types of questions you're going to have are not going to be very in-depth, because there are lots of different it's a pretty big range of these things. So we're not going to memorize any reference points or any numbers. It's just very qualitative. The same thing with this. We're going to look at the intermolecular attractions or the intermolecular forces. These intermolecular attractions, what causes these things to be so sticky? So we call them IMF, intermolecular forces. These could be repulsions or attractions. Typically, we just look at the traction part of it. And so IMF, intermolecular forces. It doesn't even have to be between molecules. It can be between atoms as well. So let's take a look at the first one here. We have the dipole forces. Dipole forces would be, let's say, if we looked at HCl. HCl has a dipole. Chlorine's more electronegative, so it's going to go like that. So this is one way to draw the dipole. The other way of drawing the dipole is using deltas. And so the chlorine would be delta minus, the hydrogen would be delta plus. And so what causes the HCl molecules to stick to one another are dipole-dipole attractions, like this over here. And so they'll want to line up. And so the negative end of this HCl will want to line up with the positive end of an adjacent HCl, like this. Or like this here. And so with the intermolecular attractions, we usually show those as dotted lines. We have dotted line here, dotted line here. These aren't bonds, so this whole thing's moving, and so these can break and reform, break and reform. That would be the dipole attraction. The dipole attraction in HCl isn't terribly strong. HCl is normally gas. But if you cool down this gas and get the HCl molecules moving slowly, then these attractions can take place. And eventually, if you cool it down enough, you can liquefy this. That is, the attractions will be greater than the kinetic energy. And so that's what we have. So in solids, the attractions are going to be the strongest. What we say when we look at solids versus liquids versus gases, well, HCl is a gas. So HCl is a gas. When it's a gas, then what we say is that the kinetic energy is greater than the IMF. If we have solid HCl, then the kinetic energy is less than the IMF. And so in solids, let's say you've had solid HCl, then the attractions are stronger than the kinetic energy. And what I can do is I can increase the kinetic energy by heating it up. Eventually it's going to melt. When it melts, the kinetic energy is about equal to the IMF, pulling it together. And so here, the solid, you cool it down enough that the attractions can dominate. And then as you heat it up, you'll form a liquid. And then as you continue heating it up, you'll form gas, where you completely overcome the IMF. The strength of the dipole, the bigger the dipole, the stronger the force. Dipole force. So the bigger the dipole, the stronger the force. Yeah. So we've got a bunch of numbers here. So this is just comparing this N2, which has no dipole, versus something that has a dipole. And so when we compare those two, we see that something with a dipole has a higher boiling point. Now this is minus 196, so this is a little tricky. Minus 196 is down here, minus 192 is warmer. And so it requires more energy to break apart carbon monoxide than nitrogen. if this were liquid, this is boiling point, so we're taking the liquid here and overcoming the IMF that is breaking apart the molecules with kinetic energy. All right, here we have silane versus phosphine, or silicon tetrahydride versus phosphorus tetrahydride. Silicon tetrahydride is tetrahedral, and it's going to be nonpolar. However, phosphine or phosphorus trihydride is trigonal pyramidal, like ammonia, and it's polar. And we look, the polar molecule has a higher boiling point, so minus 112 down here, minus 88 is higher temperature. And germane or germanium tetrahydride is tetrahedral, it's nonpolar, versus arsenic trihydride is trigonal pyramidal, which is going to be polar. And so again, higher boiling point. And here, bromine versus ICL, iodine chloride, iodine monochloride, however you want to name it, monoiodine monochloride. Since this is a polar, it has the higher boiling point, 97 versus 59. These are degrees C. So in terms of boiling point, all these boiling points are below room temperature. So all these species are gases. N2 is a gas, CO is a gas, silane's a gas, phosphine's a gas, germane's a gas, arsene's a gas. Those are the common names for that. However, bromine is not a gas. Bromine's boiling point is 59. We're at 25, normal, so bromine's going to be a liquid. It hasn't vaporized yet. So bromine's a liquid. ICL has a boiling point of 97, so ICL is a liquid also. So these two are liquid. So liquids have stronger IMFs than gases. But these numbers, don't bother memorizing any of these numbers here. And that's a lot of data just to show one trend. The more polar it is. All right. So the first one's called dipole. And the dipole is, we call this a permanent dipole. So HCl, H2O, H2O is bent. And the dipole for H2O would be pointed towards oxygen like this. This is a permanent dipole as well. The permanent dipoles we should call the average dipole. Because what happens is the electron's always moving. So when we look at the electron cloud is not static. The electron cloud is moving, and here we have two electrons. Chlorine's more electronegative, so the electrons tend to spend more time closer to chlorine than to hydrogen. And so what happens is it creates a polar bond. A polar bond will show this kind of asymmetric distribution of the electron cloud. And therefore, we could say this end is delta minus, this end is delta plus here. But what happens is, this is the average. What happens is that the electrons are not static. So if we look at the position of the electrons, sometimes the electrons are going to be like this. You know, sometimes the electrons might be closer to hydrogen. We have two electrons in the bond. If the two electrons are closer to hydrogen, then what happens to the dipole? The dipole shrinks down. And so here the dipole's shrunk down. Maybe if the two hydrogens get very close, the two electrons get very close to hydrogen, it can go even smaller. Or the opposite could happen. Let's say if the electrons are much closer than normal to chlorine, If the electrons are much closer than normal to chlorine, then it will concentrate the electron cloud more on chlorine here. So in this case, the dipole is bigger. And so the dipole fluctuates depending on how the electrons are moving. And so what we call this an instantaneous dipole. And so in one instant in time, both electrons are close to hydrogen, the dipole shrinks. This is the average dipole here. In the next instant of time, both electrons decide to go closer to chlorine, making the dipole even bigger than average. And so what we do is we just average all these instantaneous dipoles out, and then we get the permanent dipole. So the permanent dipole is the average of all the instantaneous dipoles. However, if we go looking here, nitrogen has no permanent dipole. And how do we explain the stickiness of nitrogen? So this comes to number 2. Number 2 deals with instantaneous dipoles. Your book just calls it induced dipoles. These instantaneous dipoles like this have a net, magnifying effect on the attraction. Even though it could go smaller, the net is more attraction. When we look at nitrogen, both nitrogens are the same electronegativity. This is a triple bond. And so, time average, we expect a symmetric distribution of the electron cloud. Both nitrogens pull evenly, like this. And so there's 0 permanent dipole or 0 net dipole. And therefore we call it nonpolar. But there's 6 electrons there. And so in one instant of time, the electrons might move more towards the right nitrogen. So if the electrons move more towards the right nitrogen in one instant, they aren't going to stay like this because it's not so stable. But this is like a wave, here. Thing. And so all of a sudden moved closer to here. Well, it's not going to stay like that. It's going to push back. But in that one instant of time, we've generated the dipole. And so this is called an instantaneous dipole. Now, the instantaneous dipole could be bigger or could be smaller. It's fluctuating. But if we add up all these instantaneous dipoles, here it's attracted to the right, it could be attracted to the left. When we add up all the instantaneous dipoles, we get 0 net dipole. This is time average. And so in one moment of time, we have a dipole like this. Well, if we have an instantaneous dipole like that, and we have another nitrogen molecule next to it, so let's say there's another nitrogen close by, like this. If there's another nitrogen close by, what that's going to do is it's going to induce a dipole. So first we set up an instantaneous dipole. This instantaneous dipole doesn't live for very long. So this is going to be delta minus over here. This is going to be delta plus. Now the electrons over here are going to see this delta minus. They're not going to like it. They're going to want to go to the other side. And so if they go to the other side, then that makes the electrons more rich on the right, and less rich on the left. And so this is going to induce a dipole here. And so this instantaneous induces a dipole like that, whereas if there's nitrogen over here, it'll induce it, where the electrons are attracted to this positive charge here. Instantaneous induced dipoles, these are called London forces. And they're just temporary. So here, this could be like two helium atoms. When we have two helium atoms, the electrons are in the 1s, and we expect a spherical distribution. But in one instant of time, maybe this is hydrogen, because let's say there's one electron here. Or it could be helium. In helium, two electrons maybe are on one side of the atom. If two electrons go on the top side here, then that's going to leave the bottom side more positive. It's not going to stay like this because the electrons are going to want to separate again, so they'll go from here to that. But what's going to happen is, if we have an instantaneous dipole set up in this atom, that's going to induce a dipole in the adjacent atom. And so this is what we see. Now, this doesn't last very long. This happens in one instant of time, and it's gone in one instant of time. But it's present enough that this becomes a significant attraction. So instantaneous dipole, induced dipoles are significant. And that means that gaseous nitrogen will actually stick to each other via these instantaneous induced dipoles. And that's why this, if you cool nitrogen to minus 196 degrees C, nitrogen gas to minus 196 degrees C, it condenses into a liquid. And so we can have liquid nitrogen at temperatures below 196 degrees Celsius. And the nitrogen is being held together by instantaneous induced. We get these attractions that don't last very long, but we'll have attractions here between the molecules. All right, so last intermolecular change that we're going to cover here will be the hydrogen bond. So this will be number 3. Hydrogen bond is an unusually large dipole. The hydrogen bond. It's not really a bond. Hydrogen bond is an INF, not an actual covalent or ionic bond. The unusually large dipole can only happen when hydrogen is bonded to fluorine, hydrogen is bonded to oxygen, or hydrogen is bonded to nitrogen. Hydrogen bonded to fluorine is going to give us the biggest permanent dipole. And so that's going to have the biggest delta plus and the biggest delta minus. Fluorine's the most electronegative. The second most electronegative element on the periodic table is oxygen. And so we expect a little bit smaller delta plus and delta minus. And the third most electronegative is nitrogen. And so a little smaller here. But these are still very large compared to other dipoles. And so these are still very large dipoles. And so things that hydrogen bond are have strong IMFs. This is a really interesting video I saw yesterday. You want to see this? Shows some hydrogen bonding, the importance of hydrogen bonding.
We are looking at the turning gamma subunits and the epsilon subunits. and there's the C ring in the membrane. The F1 complex is outside of the membrane, while the F0 complex is embedded in the membrane. There's the stalk, including the delta and the B subunit. The alpha subunits are shown in light pink. The beta subunits are magenta. In the middle, the central stalk is rotating. The B subunit stabilizes the hexamer, which means that the hexamer can't rotate. We will now look at a rendering of known structural states and the conformational changes that are happening. The beta subunits are seen as a ribbon diagram. The ADP and inorganic phosphate diffuse into the active site, and the ATP has just been released. And simultaneously, a conformational change occurs in the beta subunit. If we zoom into the active site, we can see the molecular structure of substrates and the chemical reaction. Here is ADP with its two phosphates. They are all held in place by a network of hydrogen bonds, mediated by the amino acids in the folded structure of the beta subunit. Hydrogen bonds stabilize the base and the sugar, but really primarily the base. There's also a magnesium ion that plays a critical role in not just stabilizing, but also neutralizing the charge of the phosphates. Notice the conformational changes that are happening when the inorganic phosphate comes in. There is the promotion of a planar transition state. Synthesis of a new phosphodiester bond is catalyzed, and then the subunit switches to the open conformation. Upon this reconfiguration in the beta subunit, ATP is ejected from the active site. The enzyme then resets and restarts the synthesis of another ATP molecule. This is a summary of the events at the active site. It is also intriguing just how the C ring rotates. We can start with the analogy of a water wheel. We can easily grasp the idea of how a water wheel rotates. It's driven by the flow of water, allowing the wooden fins to go in a particular direction. Thus, the rotation happens in a specific direction. If the water was to flow in the opposite direction, you would see rotation of the water wheel in the opposite direction. Here we see the C ring and the A subunit. We don't know the full structure of the A subunit, but we know that there's an access channel for protons on the A subunit right in the intermembrane space. And there's a separate egress channel for protons on the matrix side. In this animation, you see protons flowing out from an interface between the C ring and the A subunit. But what drives the specific direction of this rotation? For example, if we were looking down, it is always a counterclockwise rotation. Why and what drives that? On each of the C subunits within the C ring, there is a proton binding site. Notice the high concentration of protons on the intermembrane side and their flow to the lower concentration on the matrix side. Protons load.
So yeah, the protons will want to flow from higher concentration to lower concentration. Yeah, this is the cell membrane here. So that's what's driving this.
From the highly concentrated intermembrane side onto the C subunits. And they are released on the matrix side where the concentration of the protons is low. But why can't protons go around the other way as well? In principle, just as in the water wheel analogy, the C ring should be able to rotate in either direction, shouldn't it? There are two interconnected reasons for this unidirectional movement. The amino acid side chains in C subunits would repel the bound proton, so that when a proton loads from the intermembrane side, the C ring cannot rotate back in the opposite direction because it is energetically unfavorable. Rotating counterclockwise, on the other hand, is energetically favorable because there are no repulsive interactions. Remember, there's a...
So basically, when you're adding the proton, it's changing the charge. So if you try to rotate it this way, then it's going to hit the positive charges that just attach to that and prevent it. Positive and positive would repel. So this is all just electrical interactions.
Concentration gradient that favors binding of protons on the intermembrane side and the release of protons on the matrix side. So in summary, the proton gradient determines the direction of the rotation, favoring movement in the counterclockwise direction of the C ring. This avoids unfavorable interactions with the amino acid side chains of the C ring.
And then ATP is the fuel for the cell. basically. And so this is just synthesizing the fuel from ADP. It's pretty interesting here. Okay, I think we're about out of time. Today's the day, so I'll just end it here.